In this video, we'll be going on a journey to understand one of the most fundamental concepts in science and finance, the random walk. It's a beautifully simple idea that describes everything from the jittery motion of falling rains in water to the unpredictable fluctuations of the stock market. We'll start with a simple analogy. Simulate random walks in 1 and 2 dimensions using Python. Uncover the deep statistical properties and finally connect it all to the famous random walk hypothesis in finance. So, what exactly is a random walk? It's a mathematical model for a path that consists of a series of random steps. The best way to visualize this is with the classical analogy, the drunkard's walk. Imagine a person who is so intoxicated that every step they take is in a completely random direction. The path they trace out is a random walk. The core question we want to answer is, after 100 or 1000 steps, where are they likely to be? For this to be a true simple random walk, it needs two key properties. The first property is the Markov property, or memorylessness. This means that the next step depends only on the walker's current position, not the history of how they got there. The walker has no memory. Every step is a fresh start. The next property is stationary and independent increments. This just means that each step is chosen from the same probability distribution, and each step is completely independent of all the others. Now let's start in one dimension, a simple number line. A walker starts at 0. At each step, they can either move one step to the right, which is denoted by a +1, or one step to the left, which is denoted by a -1 here, each with a 50% probability. This is called a symmetric random walk. So let's simulate this in Python. We'll create a function that generates 1000 random steps, either -1 or 1, and then we'll use a cumulative sum to track the walker's position over time. And here is the path of one walk. As you can see, it's completely erratic and unpredictable. It wanders up and down with no discernible pattern, so a single walk doesn't tell us much. The magic happens when we look at a collection of many random walks. That's when deep predictable patterns emerge. There are two critical statistical properties. The first, the expected position. After any number of steps, the average position of a symmetric random walker is exactly where they started, 0. For every walk that ends up far to the right, there is another that ends up far to the left, and they cancel each other out on an average. Second, and the most important takeaway, is the variance and expected distance. The variance of the walker's position grows linearly with the number of steps. This means the standard deviation, which is a good measure of the walker's expected distance from the start, grows with the square root of time. This is the famous square root of time rule. It means to double your expected distance from the origin, you don't walk for twice as long. You need to walk 4 times as long. The further you get, the slower your progress away from home becomes. This is a universal feature of the diffusive processes. Now, let's verify this. We are now going to simulate 10,000 different random walks, each 1000 steps long, and look at where they all end up. So this snippet does the exact same logic. So now, if we run this is our result. Look at this histogram of final positions. It forms a perfect normal distribution, which is the direct consequence of the central limit theorem. Now let's check the numbers. The average final position is -0.0172, which is almost exactly 0, just as predicted. The standard deviation of the final positions is about 31.6, and the theoretical value, the square root of 1000 steps, is also about 31.6. So the simulation perfectly matches the theory, right? Now, let's expand to 2 dimensions. Our drunkard can now move north, south, east, or west, each with an equal probability. So if you run the snippet, we'll get a simulation of a 2D walk with 5000 steps. So here, the green dot is the start and the red dot is the end. To prove that this walk is completely random, if we run this function multiple times, we can see that each time the path is different, proving the randomness of the walk. It looks like a tangled piece of string, again completely random, but it allows us to ask a fascinating question. Will the walker always return home? The mathematician George proved a startling result. A random walker in 1D and 2D is recurrent. They are 100% guaranteed to eventually return to their starting point. But a walker in 3D is transient. There is a high probability that they will wander off and never return. Think of it this way. A drunk person lost in a narrow alley or a large field will eventually stumble back home, but a drunk bird let loose in the sky will probably fly away forever. There is just too much space in 3D to get lost in. This brings us to the most famous application of this theory, the random walk hypothesis in finance. It's a cornerstone of the efficient market hypothesis. It's a cornerstone of the efficient market hypothesis. The hypothesis states that stock price changes are random and unpredictable. Why? Because in an efficient market, all available information is already baked into the current price. Therefore, future price movements can only be caused by new information or news. And since news is by its nature unpredictable and random, the price changes that follow must also be random. Now, let's see if the daily returns of the S&P 500 using the SPY ETF look like the random steps from a simulation. So in this snippet, we download the open high-low close data of the S&P 500 stock from 2000 January 1st to 2024 December 31st. And we calculate the percentage change in close of each day. And we plot the histogram. So here is a histogram of the daily percentage returns of the S&P 500 over the last 25 years. Looks familiar, right? So distribution sharply peaked around the mean, that is very close to zero, just like the distribution of steps in a random walk model. This shows that on any given day, the stock market is almost likely to go up or down, which is a strong evidence consistent with the random walk hypothesis. So, the random walk is a deceptively simple model that describes the nature of cumulative randomness everywhere. From its origin in describing the physical phenomena of the Brownian motion to its central role in the modern finance, it teaches us a profound lesson. While any individual path is completely unknowable, the collective behavior of many random paths is highly predictable and follows deep statistical laws, with the most important being the square root of time rule. It is a beautiful example of order emerging from chaos.